yesterday we looked at weak gravitational waves as approximate solutions to the Einstein equations. And it turned out to be convenient to split up the full space-time metric G mu nu to a constant piece plus a perturbation, you could say. And the constant piece is usually taken to be the Minkowski metric. And this, in the linearized, for the linearized theory to be applicable, this is the entries of F mu nu is supposed to be small, much smaller than 1, so the entries of the Minkowski metric. And then I told you that by an appropriate a choice of gauge fixing, that is putting additional conditions on these F mu nus in order to get rid of kind of a redundancy that is implied by kind of coordinate invariance, you could bring the source-free Einstein equation, so without any external matter sources, to the simple form box F mu nu equal to 0. So that's the wave equation, which we know how to solve in a straightforward manner. We also looked at the effect. I mentioned the effect this has, a passing gravitational wave, on a circular array of test masses. And since someone asked me afterwards, so the setup is you have some test masses, and when the wave passes through, they will experience gravitational forces to change their overall, the shape of that array, kind of to something elongated, oscillating in, say, as I do on the board yesterday, become kind of narrow, and then go back to circular, and then become kind of extended horizontally. And this, of course, they do this periodically as the wave dictates. So these are genuine physical effects. And of course, they tend to be, for gravitational waves that come by here, they tend to be extremely tiny. So the detectors that have been built to look for these kind of effects still haven't seen them, although they are already ultra sensitive. Then we looked at more of the theoretical description, also at these polarization tensors. And really, the reason for doing this is to exhibit now what kind of physical degrees can I get, kind of a feel for what these physical degrees of freedom are, at least in this linearized case. Can I exhibit them explicitly? And we saw that that could be done with an appropriate choice of variables. And this really was to prepare for the quantization of these linearized degrees of freedom. And the last thing I did yesterday was to exhibit what happens to kind of these polarization vectors that dictate, essentially, so you have two linearly independent choices for the gravitational waves. And there were various ways, of course, since it's a two-dimensional space, I can choose a basis in the set of polarization tensors. And one of them was the one I had on the blackboard first. That was the cross. Sorry, what was the first name? The cross polarization. And what was the name of the first one? No, whatever. And then the plus. Thank you. The plus and the cross polarization. And by taking linear combinations, I could then make into a right circular and left circular polarization. But that's just a choice of basis. And we then looked into how these modes behave under a rotation in exactly kind of the plane of these test masses. So the plane perpendicular to the direction of the gravitational wave in a three-dimensional spatial sense. And then we found that it's mapped. Well, this you could already see by examining kind of this array of test masses. It was mapped onto itself under a rotation of 180 degrees. Not 360, but only 180. And that's a hallmark of a particle of helicity plus or minus 2. What we're going to do today is to look at the the quantized version of this picture. And of course, we'll meet this helicity again in the form of a property of wave functions, elements of a Hilbert space of the linearized theory as the spin of particular modes of the quantized linearized gravitational field. So this is kind of the setting. And we look at some of the ingredients. I remind you of some of the important structures that appear that help us understand what goes on. And of course, underlying that is really Minkowski space. So in this linearized version of thinking about things, Minkowski space is just where everything takes place. And in this approximation we are looking at, there is no back reaction of the dynamics of the gravitational field back on eta mu. So it doesn't, its geometry in that approximation will always stay that of flat Minkowski space. Okay. So, and the Hilbert space where everything takes place, where the dynamics takes place, is kind of the standard Fock space now for the gravitational linearized modes. So I'll go relatively quickly through this. Well, I hope that it helps you put this into context. You may have, of course, you should recognize bits and pieces of what I'm going to do from one of your quantum field theory courses. Now, what's a kind of lightning review of the Fock space representation? How do I get there? Well, the quickest way is to start kind of with quantum mechanics of the one-dimensional harmonic oscillator. And what the Fock space is basically taking the Hilbert space of that oscillator and kind of apply it, use it for each single mode of the quantum field theory. So that's a standard construction. Now, where do we start from in one-dimensional mechanics? Let us look at the one-dimensional harmonic oscillator with, for simplicity, the mass set equal to 1. Let me look at this in the Hamiltonian framework, where I have a pair of variables x, position, and momentum p. And I have a Hamiltonian that is just quadratic in these variables p squared divided by 2, because I've set m to 1, plus omega squared x squared divided by 2, where this is the frequency of the harmonic oscillator. Now, how can I think of the quantization of this simple system? Well, classically, I should write this out, there is an algebraic structure on the phase space, two-dimensional phase space spanned by the x and p, which are the Poisson brackets. So, and the algebraic structure is characterized by giving you kind of the Poisson brackets of the elementary coordinates on phase space. And this is just given by 1. And of course, x with x is 0, and p with p is 0. And from this, of course, you can deduce by associativity all other Poisson, classical Poisson brackets of any classical phase space function. Now, one way of thinking about the quantization is that this relation becomes kind of the elementary commutator relation, the so-called canonical commutator of self-adjoint operators x hat and p hat corresponding to these classical phase space functions, x and p, this being equal to I, where now an h bar, of course, makes an appearance in the quantum theory. Now, one can go to one can redefine kind of the basic operators of the quantum theory to start with in a relatively unmotivated way, but of course they turn out to be extremely useful, by taking complex linear combinations, as usual, with appropriate constant coefficients of the x hat and the p hat, like that. So that's the A. And then there is an A dagger, which is simply the complex conjugate of this thing, or rather the adjoint. So the operators are adjoints, A dagger, by definition, or construction, you could say. Now, X and P are both self-adjoint, so they're equal to X and P, minus I divided by square root 2 omega P hat. Now, and if you now work out what the elementary commutator brackets are between those two, of course you find that A commutator with A dagger equal to H bar. So far, so familiar, I hope. Now, pay attention. So A is, of course, not self-adjoint because this is its adjoint. So it doesn't have an immediate physical interpretation. I mean, it doesn't have a real spectrum, right? But clearly, it encodes all the information there is in this very simple quantum mechanical system. And H, the Hamiltonian H, is now given by H hat, quantization H bar omega A dagger A plus 1/2. And its eigenstates can be labeled by a integer capital N. And the spectrum of H, the quantum Hamiltonian, of course, having that amounts to having solved the dynamics of this simple quantum harmonic oscillator, is given by N plus 1/2 H bar omega, and N runs from 0, 1, 2, etc. to infinity, just through all positive integers. So note that the spectrum is equidistant, right? To jump to the next eigenvalue, I always add an H bar omega. So that's just a physical property of this very simple one-dimensional harmonic oscillator. The ground state, I have to put this down. So the eigenstate of lowest energy is just this one, but you see it has a non-vanishing ground state energy. I mean, that's the famous zero-point energy of the system. And what other condition does the ground state satisfy? It is annihilated, as one says, by this operator A hat. And, of course, H hat acting on it is equal to H bar omega half times this eigenvector itself. Now, I mentioned in passing, I pointed out that this is equidistant. Now, the fact that the spectrum is equidistant suggests an alternative interpretation of this simple system, namely as that of a bunch of identical particles, where now the N just counts how many of them I have, where each of them contributes an energy bit of h bar omega. So it's clearly only the fact that the spectrum is equidistant that allows me to do this. But this is exactly an interpretation, of course, one adopts now when one scales this up to kind of a Fock space representation, so a representation of a field theory. So this suggests an alternative interpretation where now n I can think of as a state of n indistinguishable, I should say, particles. Each of them contributing an energy h bar omega. Now, next step is, of course, what sometimes it is called, nowadays not so much anymore, second quantization. Now, why is that a useful observation for me now taking the next step to, say, quantizing a scalar field? Now, let's have a look at a kind of free massive scalar field on Minkowski space. This, of course, satisfies the Klein-Gordon equation, which, of course, is familiar to you. It is box minus m squared. Now my scalar field, let me call this phi. So I should have called it phi already here. If I write this out in components, minus dt squared plus nabla squared, nabla vector squared, minus m squared, it looks like this, of course. And of course, it's nice, it's linear in the field. This can be solved by Fourier transformation, right? I make a Fourier ansatz for phi of x, and then I get for each mode, now labeled by, not by x, but by k, I get back the equation for the one-dimensional harmonic oscillator. Harmonic oscillator with omega equal to omega, now labeled by a 3-vector k, equal to m squared plus k squared. So now, of course, this is now so for every such vector k, 3-vector k, and we can separately quantize each mode according to what we did for the one-dimensional oscillator, and we'll get to creation and annihilation operators, as they are called now, a hat dagger, for each mode k. So I have to keep that as an argument here, and a hat k. Now, the reason why I'm calling them creation and annihilation is, of course, that I have not adopted this alternative interpretation. You know, it's a particle of momentum k I'm creating or annihilating, and which will, of course, contribute an energy omega k now, given by this square root here. Now, obviously, they will now satisfy canonical commutation relations. But, of course, I have an infinite number of these. But they will always commute. The A and the A dagger will always commute when the arguments are different. Right? And otherwise, they will give the familiar, they will just give 1. And that's, of course, captured by the right-hand side, which is just a Dirac delta function of k minus k prime. So these are the canonical commutation relations of these k modes of the scalar field. Now, what is the kind of ground state of the system? Well, it's the no particle state. So when no particle, I mean none of the k modes has any particles in it. Okay, so it's being is also called the vacuum state in the context of field theory, and it's annihilated by all the k's, a's of all the k's to 0. And now applying one A dagger operator on the vacuum produces kind of a one particle state with label k. And the space of all these one particle states is a Hilbert space. So this is called the Hilbert space. Of one particle states. If I want to create a two-particle state, then I apply an A dagger twice. And of course, in generality, they will have different k arguments. So, for example, k prime, A head of k prime, sorry, A head dagger of k prime and A head dagger of k applied on 0 gives me a vector k, which I label like this, and it's a two-particle state. And it's an element of the tensor product of two one-particle states, which I also can write in this way, an H cross, tensor product 2 as a superscript. Now, what is my Fock space? Well, the Fock space is the space I get by adding up all these tensor products so that I can have particle states of any number. So let me call this curly F, associated with my original Hilbert space H. This is the direct sum from 0 to infinity of all these this tensor product spaces with arbitrary numbers of terms, and this is Fock space. Now, this is a slight abuse of language. So usually you consider subspaces of Fock space that are given when you talk about bosons, given by the totally symmetrized tensor products here, or when you're talking about fermions, the totally anti-symmetrized parts of this. So these are appropriate subspaces of Fock space. And they are now, they are the habitat of perturbative quantum field theory. Any operator that you have acting on these Hilbert spaces can in principle be written, as a function of these elementary A daggers and A hats. These elementary operators. For any given type of field or particle, you may have additional quantum numbers. So there might be additional labels. And this is, of course, also the case for gravity. When you do this for the scalar field, there are no additional labels. But we have already seen that the classical gravitational waves, they have this other property, helicity, right, and polarization. So they have additional physical information. And of course, this I have to carry over to the quantum theory also. So these labels, of course, will now show up again in the quantum theory. Now, how do I get to this helicity label? Well, let me go one step back and remind you of the fundamental symmetries, as I have already emphasized, go always into the construction of quantum field theories, at least perturbatively, on Minkowski space. So there is this global 10-parameter symmetry that maps Minkowski space into itself, and where we require all our relativistic quantum fields to transform in a covariant manner. So that's one of the kind of essential properties we require as a physical input. So that leads us, of course, to relativistic field theories, or now for our purposes, it plays the same important role in quantum field theories. And of course goes by the name of Poincare symmetry. Now, completely explicitly, what did this look like? The global symmetry we have simply acts on the points of Minkowski space. So let me, as usual, just call them X mu's. So it's a global symmetry of that Minkowski space. And let's then see afterwards what they do to the fields. So that's just the way a general Poincare transformation works. It maps you from a point X mu to a point Y mu, which consists of a linear piece in X, which is just a Lorentz transformation. So a generalized to this indefinite metric, Minkowski metric, a generalized rotation given by a 4x4 matrix capital lambda mu nu, operating on X nu. And here, to get from the Lorentz group to the full Poincare group, you add translations in the 4 independent directions. And of course, those translations, they're parameterized by 4 parameters. So how many parameters are in here? 6 generalized rotations, so 3 spatial rotations and 3 space-time boosts, and 4 parameters which correspond to arbitrary linear translations in the 4 coordinate directions. So I have a 10-parameter family of transformations. And the reason why they're called global transformations is that they act in the same way and simultaneously on all the X mu's. Right? So there is no X dependence here or here. So they're just 10 parameters, and they will do something to Minkowski space. Either rotate it in its entirety, or boost it in some direction, or just translate it in one of the directions. So stuff happens to all of Minkowski space. That's the global nature of these things, just to remind you. So this is a 10-dimensional non-compact Lie group. I'm not sure how much you've heard about Lie groups and algebras so far. Has any of the courses covered that, or some of it? Yes, some nodding. So it's non-compact because some of the parameters are non-compact. These are clearly non-compact, and the boost parameters are all also non-compact. Of course, the angles in the spatial rotations are compact, but this is a non-compact Lie group. So that's the group of symmetries of Minkowski space, and often you are given it not in terms of kind of how the group acts, but in terms of the algebra relations satisfied by the generators, the infinitesimal generators of the group. So they will, if I expand a general group element around the identity, it is of the form a matrix, unit matrix 1, plus generator times some coefficient. So that's kind of a linear, it's a Taylor expansion, and kind of the first order kind of linearized object that generates are the Lie group generators, or Lie algebra generators, which is one of the same thing. So you have now 10 of them, and I call them capital P mu. These are the generators of the 4 translations, P for Poincaré, and I call the generators of boosts and rotations capital J lambda mu. So I'm not going into great detail, but I remind you of what their characteristic algebra is. You see, I mean, in order to understand, what Lie group or Lie algebra I'm looking at, I just have to look at the defining relations. And essentially, they're given to me by commutators of these generators. So here, what characterizes the Poincaré group is all pairs of commutation relations. P mu with a P nu, 2 translations, commute always. Now, what do you get when you take the commutator of a generalized rotation with a translation? Well, that's non-zero, and you get the following linear combination: I, imaginary I, eta mu nu, P lambda minus eta u lambda, capital P nu. Well, this is, of course, the Minkowski metric. And the most complicated relation is J mu nu, J rho sigma. Okay, folks, can I say something in general? I'm really allergic to people coming and going while I'm lecturing. So please either stay here, right, or stay out, but don't, come and go. It's very disturbing for me as a lecturer. And, I'm here to give you a complete story, right? So if you think, okay, well, I'm happy to miss 10 minutes. Well, I've structured the lecture so that there is a logic in it, right? So please be here. If you have to be late, stay out, and look at it on the, on the web. Good. Now, so this is again a linear combination now of the J's. So J's with J's give you back J's. Eta nu rho J nu sigma plus eta sigma mu J rho nu minus eta nu rho J mu sigma minus eta sigma nu J rho mu. So that's, of course, really long and cumbersome. Now, some properties of this. I mean, how do I see that these are the commutation relations of a Lie algebra? Because the right-hand sides are linear with constant coefficients in the generators J and P themselves. Okay, so that's just a Lie algebra. And it's not completely invariant, but you can redefine, you can take linear combinations of these, so which might change the right-hand side. But of course, the statement is you can always choose linear combinations such that the algebra looks like this. And it will only do that if this is really the algebra of the Poincaré group. Okay. Now, many things one can say about this, but we'll be interested in how representations of this group, so that are implementations of the group and algebra relations, acting now on, say, wave functions in some Hilbert space, how they act, say, in the first place, on elements of this Fock space. And they have a unitary action. Of course, the details will depend exactly on what kind of fields I am looking at. So on states psi. And that we now generically call kind of the unitary matrices that will act on, you know, whatever scalars, vectors, spinor fields you have here by capital U. And of course, it will still depend on those 10 parameters I introduced above. Okay, in some way, but these will be unitary matrices. And of course, the whole point, which I already mentioned yesterday in passing, is that you can actually classify different types of fields by how they transform, by in what unitary representation of the Poincaré group they transform. So that's actually, like you could almost say, that's all there is to the different types of fields. That's what distinguishes them, the way they transform under Poincaré transformations. That makes them, and that, well, how can I classify, I mean, what parameters classify distinct unitary irreducible representations? It's essentially the mass and the spin of the field. And these are just properties that are intimately related to the properties of the representation theory of this group, this non-compact Lie group. Now, so let me just write this down. So we can classify fields and particles according to their transformation behavior under unitary irreducible representations of the Poincaré group. And so the classification goes according to mass and spin, essentially. So in a way, you can think of that as a purely mathematical exercise in representation theory. And the person who first made this classification was Wigner, back in the earlier days of the 20th century. So the way to arrive at the classification, or the way to understand what mass and spin a particular representation corresponds to, is to identify particular objects, so-called Casimir invariants or Casimir operators, which are quantities that are quadratic in these generators and commute with all the elements of the representation. So they lie at the center of the representation, you could say. And because the representation is irreducible by assumption, so it cannot be split up in smaller pieces that are themselves representations, every operator that commutes with all the elements has to be a multiple of the unit matrix. And, of course, it doesn't have to be the unit matrix, so exactly the eigenvalues it has, so the multiple of the unit matrix that appears gives you exactly, say then, the mass in case of one of the Casimir operators and the spin in case of the other Casimir operator. Okay, so this is just little bits and pieces of information which you will be able to do something with if you have, heard more about this story before. So let me just say this in passing. Now, what happens to our one-particle states? Now I'm thinking of gravity, of linearized gravity. So let me give them a momentum label that clearly comes already from the simple Fock space construction, plus now an additional label, which I call sigma. And that sigma will become the spin in a moment. So how do these transform? Now I go front up. Oh, that one is fixed. Yeah, I have only 3 ports. Yes, I will fill this, but I put it up a little bit just for me to write on. Oh no, it doesn't move, you say. Yeah. That's too bad. Okay, I have to move, if Moses, how is it? Okay. Now, sorry, yeah, I didn't want to be specific, really. Now, this is the kind of the generator of the translation in the representation operating on my Fock space states for linearized gravity. They are eigenstates of the momentum expressed by this eigenvalue equation. Now, where does this sigma make an appearance? Well, not yet, not in the next relation I'm writing down, but in the one after that. So if I now operate on this with a translation, right? So I've set the lambda part equal to the identity, so no rotations, no boosts. Then again, this is unitarily implemented, on such a state, P and sigma. This is unitarily implemented by a phase factor minus I A mu P mu operating on P sigma. So you see, P mu upstairs. And you see, of course, if I have a big translation, right, that will just factor into a different phase factor. Now, for the classification, it makes a difference of whether your field is massive or massless. So that will amount to different subcases in this analysis I just mentioned to you exists. I'm not doing the analysis for you here. And for massless, the massless case, which is relevant for us here, for these massless long-range gravitational excitations, one looks at another object, another operator, which is essentially a quantization of J vector P. J are essentially J, so this has 3 indices, so is up to Ji is up to some factor, which I haven't looked up, sorry. An antisymmetrization of these guys, something like that. Okay, so these are the generators I used here. So, for example, J3 comes from spatial rotations in the 1-2 plane. Right, so this is how it works. So this W, this here has eigenvalues. So let me write, this is a physicist equality sign. P modulus, so of the 3 vector, momentum vector, times h. And this is exactly the helicity we met in the classical analysis. And so this has the interpretation of now the component of the angular momentum say, so let me be specific, what I want to do in one of the directions. Let me choose it along the 3 momentum, say component of angular momentum, say, along the 3 momentum, k vector given by 0, 0 omega, and J3 operating on, well, I should call this P again, excuse me, and not K, although it doesn't matter. This gives me exactly sigma P vector sigma. So I take the one particle state here along the vector P, and it will give me the eigenvalue will be exactly this label here. And if I now look at the appropriate kind of spatial rotation, you know, say in the 1-2 plane, how this unitarily acts on this state, it will be up to some proportionality factor. So let me write it like this. Let me write it like this. It will give me a phase factor e to the I sigma. That's exactly the helicity. And then kind of the theta. The theta now just refers to the angle in the 1-2 rotation around the axis here I'm considering. Well, that is somewhat inherent in this Poincaré element I'm looking at. And it will give me, it's not exactly, this is not an eigenvalue equation, because it will give me the translated or the rotated P here. So vector over everything times the sigma. So, and you see here, this is exactly analogous to the relation I derived yesterday to how the classical modes of this field transform under a rotation. And this here, we also there call the helicity. So this reappears now here as a label on the Fock states, with very much the same geometric interpretation. Okay. No, this I have some space to here. Yes, okay, so this is, of course, the modulus of this helicity is now what we call the spin of the particle. And now, kind of, we have completely understood how the Fock states for the linearized gravitational field are constructed and what properties they have, roughly speaking. And I already told you, well, there's nothing more to their properties than to tell you how they transform in the particular unitary irreducible representation of the Poincaré group, corresponding to that type of particle. So we can now go ahead and start quantizing. We can just simply, as we do even for the scalar field, now starting from the classical fields, now construct corresponding quantum operators for these linear field modes. And these are called f hat of x. And as usual, I can just write them as a as a Fourier, in the Fourier representation, with appropriately normalized integral here, 1 divided by square root of 2 e k. That's, of course, the same as omega k that we had earlier. Now, here I have not only an integration over k modes, but, of course, also a sum over polarization states. Right? These are my extra labels, which characterize my gravitons, if you like. So here I have to sum over the states with sigma equal to plus or minus 1. These are the two possibilities I have for every field mode. Now I have a coefficient, which I'm quantizing here, A hat, K sigma. Now here I have the unit polarization tensor. This, of course, is a tensorial character of those. Is, of course, exactly now encoded in an appropriately chosen basis of these polarization vectors. So these were the ones we already were looking at yesterday, the plus and the cross, etc. Of K sigma e to the I k x, four-dimensional scalar product, plus A hat dagger K sigma E star mu of K sigma e to the minus I K x. Now, this is now here the annihilation operator. And this thing here is, of course, a creation operator of the field mode with momentum k and helicity sigma. And this is, of course, a straightforward generalization of, say, what you do for when you quantize a scalar field. So that is, quantum field theory 101. Yes, question? Yes, you have to be a little bit careful because we have already specified this to be a specific subset of, say, transverse traceless modes. So you have to compensate for this. So you're completely right. I mean, these are not, I'm thinking of these now as a physical degrees of freedom. And having made, for example, a specific gauge choice like I did yesterday to identify transverse traceless modes, that's not, the gauge choice itself is not Lorentz invariant. So I have to keep track of that. Actually, the book by Kiefer I mentioned in the first lecture has a nice discussion of that. Okay, now what other information do I have to give you? Well, the canonical commutators. They are, of course, exactly like those for the scalar field, but now with an additional Kronecker delta corresponding to the two polarization states. Okay, so I have here my sigma or helicities, whatever you like to call them. A hat, A dagger hat of K prime sigma prime is now Kronecker delta of sigma prime times three-dimensional Dirac delta function K minus K prime. Now, this way of quantizing the gravitational field is exactly what people did back in the 1930s. And, of course, where they came from was quantum electrodynamics, which was in the process of being understood. And then, obviously, while gravity clearly was one of the other fundamental forces that was known by the time, people tried to apply the same kind of formal construction. This Fock type construction we illustrated here. So I want to mention kind of two names here in particular. So the Belgian physicist Leon Rosenfeld wrote down basically this linearized construction in 1930s, and around about the same time, Matvei Bronstein, Russian physicist, who wrote actually his thesis on this, more or less, had similar ideas. And I dug out an interesting article. I mean, looking into the history of things is, of course, sometimes educational, because you oftentimes see that, you know, what the kind of arguments you're giving today has been made frustratingly already by people, like, say, 80 years ago. And there's a nice a quote I found from John Stachel. He is a very well-known historian who has edited Einstein's works, amongst other things, that has written about the history of GR and quantum gravity. He points out that already by the end of the 1930s, essentially there were kind of three different types of opinions among theoretical physicists about quantum gravity. So the first group of people said, well, you just do that totally analogously with QED. You know, essentially along the lines here I started giving you here, and you know, what's the problem? Then the second bunch of people said, well, look, I mean, this is very strange. You know, I'm going to a classical, already to an approximation, the linearized approximation. I mean, that's not the spirit of full gravity. So clearly, this will not lead me anywhere interesting, you know, just quantizing these modes. And there was a third group of people who said, look, gravity is completely different. I mean, gravity says something about space-time that has nothing to do with, you know, electrodynamics. That is about, you know, real physics and stuff, you know, fields and masses and matter interacting. So we shouldn't even bother quantizing it at all. And let me quote. So he quotes, for instance, he quotes Bronstein as saying, suggesting. So this is from well, somewhere around the 1930s. So this is a Stachel quoting Bronstein. He suggested that application of the formalism of quantum field theory, which is what we have been doing here, might not yield the desired fusion of quantum theory and gravitation, calling for a, now, quote Bronstein, a radical reconstruction of the theory, and in particular, the rejection of Riemannian geometry, and perhaps also the rejection of our ordinary concepts of space and time, modifying them by some much deeper and non-evident concepts. So that could, of course, be a literal quote from anyone, any person, you know, giving a talk at a major conference on quantum gravity. And, well, depending on the flavor you've chosen. So you see, it's all, we are not the first people to have thought about it, but of course, nevertheless, the problem is still there for us to conquer. Thanks, and see you tomorrow.